Hello. So this is a multiple choice question from GATE 2023, and this question is from the part electromagnetic theory or EMT. So this question states, consider an isolated magnetized sphere of radius r with a uniform magnetization m along the positive z direction with the north and south poles of the sphere lying on the z-axis. It is given that the magnetic field inside the sphere is B equals twice mu 0 by 3 m, where mu naught is the permeability of vacuum. Which of the following statements is or are correct? So we are going to check these options one by one. Okay. So I have already made a diagram for visualization, easy visualization. So we will proceed and I would explain the things one by one. So the first option is given as the bound volume current density is 0. Now, given that uh, the magnetization is uniform in positive z direction. Okay. So let the magnetization as m equals to m z cap. Now the first option wants us to find the bound volume current density. So the bound, so this is for option A, volume current density, which is JB, is given by curl of M, and as M is uniform, so this should be 0. Why? Because as M is uniform. Okay. So that makes option A correct. Now let us check the second option. So in this option, it states that the bound surface current density has maximum magnitude at the equator, where this magnitude equals m. Okay. So you can see here in the diagram. Okay. So this magnetization m will arise due to some bound current density. Let me or surface bound surface current density. Let me call it as with the vector kb. Now we need to find the maximum surface current density or the maximum of this kb, and we need to check if this value is equal to amplitude of m or not. Okay, so the bound, okay, take 1 second. Yeah, so the bound surface current density is given as kb, and the formula for this is m cross r. Okay, where m is given as mz cap cross r. Now we know that z cap can be written in the polar coordinates or spherical polar coordinates in this form: z cap equals cos theta r cap minus sine of theta theta cap. So z cap cross r cap will be theta, right? Cos theta minus sin theta, and obviously this is 0, and here this is 1, 0, and this will be also 0. So this will give me r cap times 0 minus 0 plus phi cap times 0 minus 0 plus phi cap, and this should be 0 plus sine of theta, right? So this will be sine theta phi cap. So KB equals m sine theta phi cap. So we have defined the value of surface current density. And this surface current density, I have also shown a arrow in which direction it will be. And I have just put another surface to in order to specify the direction of this flow in another point. Okay, so nothing to do. Now at the equator, theta equals pi by 2. So theta equals 1, and thus KB equals to m pi k, and so that the modulus of KB equals to m, which is equals modulus of. So let me check the second option. Yes, the bound surface current density has a maximum magnitude at the equator where this magnitude equals m. So this is the maximum magnitude as the sine theta has the maximum value of 1 and this magnitude is m. So this option is also correct. Now let me go with the third option. It states as the auxiliary field H equals minus 2 by 3 m. Okay. So now we know that H equals B upon mu naught minus m. Okay. Now we have given that B equals 2 by 3 mu naught m. Okay. Inside the system, given that B equals 2 by 3 mu naught m, and this implies B by mu naught equals to 2 by 3 m, so that H becomes 2 by 3 m minus m, and this equals minus 1 by 3 m. Okay, so this option is clearly not matching with our calculations. Now the go with the fourth option, and this option states that far from the sphere, the magnetic field is due to a dipole moment m, where m by 4 pi r cube equals b by 2 mu naught z cap. So I think so far from here, let's say in this direction, it is here. And we already know that this b value, what is given, b z cap, is inside the sphere. It's a uniform field, but outside the sphere, uh, this sphere will act like a dipole. So there should be a dipole moment m, and we need to find the relation between m and b. So okay, let me just write down this formula. So outside the sphere, B out, whereas B in was simply B, to be given as mu naught M by 4 pi r cube times 2 cos theta r cap plus sin theta theta cap. Okay, so this is a standard formula, and this is the relation between this M is the magnetic dipole moment, and this is fine. So now we need to find the relation between this B and M. So this is the formula given, but we are going to just calculate it straightforward in a straightforward manner to check the relation between B and M. So we have B given inside as 2 by 3 mu naught upon M. Okay, and this B is also given as B Z cap equals 2 by 3 mu naught, and this magnetization vector can be given as M, which is the dipole moment, by 4 by 3 pi r cube. Okay, yeah, fine. 4 by 3 pi r cube, where r is the radius of the sphere. So you can just cut this out, and this will give me that the z cap by twice mu naught equals to m by 4 pi r cube. So this is the relation that I am getting, and this relation is the same which is given in the option D. So we can say that option A is correct, B is correct, D is correct, and C is not correct. So the correct choices are A, B, and D.